Hi everyone, welcome to this online lecture for Geography 104 for the class this October 19th, your normal Thursday class. Thank you for bearing with me as I am currently probably in Madison, maybe between Madison and Chicago if you're watching this right as it premieres at 11 o'clock. So today we are going to be finishing our discussion of soil water and groundwater. Now, before you start getting into the video, one thing I do want to mention, I'm not going to be slowing down necessarily as I go through the video. So I would suggest as I pan screens and I go to the next slide and the next slide, pause it, write everything down that you need to, and then start me again. If you're going to watch me at 2x speed, I totally get it, whatever. But I would suggest that you at least pay attention and make sure you get all those notes down. These will be really crucial as you're starting to prepare. And obviously, as I mentioned, quick reminder, after this lecture, I will have the first quarter of your study guide for your midterm exam 2 posted. So that'll be on these first 2 lectures. So stay tuned for that. That'll be posted under probably the exam 2 materials on Canvas. You'll be able to find it there at the end of the hour at 12:15. So with that, we're going to go ahead and get started. A couple of quick business items first. Obviously, your lab exam 1 is coming up next week. Make sure you are all prepared for that. You can find the exam or the lab keys posted on Canvas. You can email Dr. Joel, Dr. Faulkner, and myself with any questions you may have. So this will be taking place during your normally scheduled lab time. So go to lab as usual. You'll have your lab exam then. The exam is going to cover anything that we touched on in pre-labs and labs 1 through 5. So if you're asked, is this going to be on the exam? It's totally fair game. So make sure you're studying everything. My big suggestion is kind of try to look through what I call the greatest hits for each of the labs and think through it that way when you're trying to figure out what really to focus on and what really to study on. It's kind of help the students get an idea. So as you're going through, observations and looking at discharge in Little Niagara Creek for lab 1, lab 2, we're looking at scale and differences between scale, large and small scale maps. Lab 3, we're looking at contours and reading topographic maps. Lab 4, we're looking at energy and insolation in the seasons, so how that energy budget changes latitudinally and then what affects that on a more local scale. And then lab 5, moisture in the atmosphere, right? We're understanding specific humidity, saturation, specific humidity, relative humidity, air temperature and dew point, going up and over the mountain, Mount Doom. So think of these kind of greatest hits and take the examples that we provide you, change a couple numbers, and see if you can do it. Go up and over the mountain, figure out a couple different cities than the ones we give you, Eau Claire, Reykjavik, and Manaus, and all these others. So just change things up, and you've got a study guide, and you've got ways to practice. So keep that all in mind. Obviously, reach out if you have any other questions. What will you need for the lab exam? This is incredibly important for everyone to pay close attention to. You need a scientific calculator with trigonometric functions. You will not have access to your phone. Your calculator is a standard issue calculator that you bring. We do not have calculators for you, so you can't use your phone, and you got to bring your own. So you got to make sure you do those things. We will have rulers, protractors, and colored pencils available for you if you don't bring your own for a nominal fee. Actual money you're going to have to pay if you don't bring the materials that you need. So I would highly suggest making sure you have your scientific calculator, your official 104 ruler, your official 104 protractor, your official 104 colored pencils. Definitely bring an eraser. Do not do this in pen. And then you absolutely must make sure to bring your Goods World Atlas. We will be requiring it for the exam. If you don't have your Goods World Atlas, you don't have an ability to answer the questions that require you to use it. So we will be sending out reminders, obviously, on Monday, going into the lab exams. Bring these things, but consider this kind of the first reminder that you need to make sure you have these 6 things with you when you come into the lab exam on Tuesday or Wednesday. So getting into what we're actually going to be talking about today, we're going to be a little bit of recap from last Thursday, because we had our lecture exam this Tuesday, before we kind of go into the new material. But we were kind of talking about this idea of water as a resource rather than how it functions throughout the atmosphere. So talking about surface water and groundwater and how surface water and groundwater interact. And that's really going to be the big component of what we're going to talk about today. So the lecture is mostly going to focus on the hydrologic cycle, really soil water and groundwater. We can look at it as an example like this little diagram right here. We have a bunch of different places that water is coming in. This is a little bit specific, right? We've got a glacier on the left side of the image there. We've got swamps and puddles that collect water on flat land, drain into a stream. We've got some of that water infiltrating into the groundwater zone. We've got sheet wash, things rushing over the surface into lakes and rivers and streams. Snow or rain falling directly onto a stream. All of these are different ways that water moves across the surface or moves through the surface into our groundwater supply. We're going to learn a bit more about the nuances of that as we go on. But first, let's talk about just surface water in general. So some of the things that as you have water rushing across the surface or falling on the surface, it interacts with certain aspects or attributes in different ways. So we have precipitation, right? Things being delivered from the atmosphere to the surface, whether that's snow or rain or hail or sleet or graupel. And there's about 7 or 8 different types of precipitation that we recognize. We're just going to call this precipitation. Some of that just runs directly off the surface to our rivers and streams. Some of it evaporates from the land and from water bodies and goes back into water vapor within the atmosphere. Some of it percolates or infiltrates through our soil zone and through our vadose zones, so these unsaturated zones, and into our groundwater supply. Some of it we count as soil moisture. Some of it we consider groundwater or the zone of saturation. And a key distinction here between our unsaturated zone and our saturated zone, you might have heard the term water table before. Well, the water table is really just an expression of the top of the groundwater zone. So that's really where you get, if you're below that, you're fully saturated. Water is filling all the pore spaces of your sediment. We'll see a little bit more about that today in lecture. But the water table is just the top of that surface. Anything below the water table is considered groundwater. And then biologic material, right? Plants and other aspects intercept that rain that's coming in, and it can cause that to evaporate or transpire. You're sweating out moisture. Now, this is an idealized system here, right? We don't live in an idealized world. We modify these systems pretty heavily, as a matter of fact. We can see in this case there was a recently re-laid lawn. There's straw over it right now, and you see this big plume of sediment that has been washed off onto the road after seemingly a recent rainfall. A little bit closer look at it here. So why didn't the rain soak in? When we say soak in, we mean infiltrate. Not soak in means water is running off. We'll learn a little bit more about those terms on the next slide here. But why didn't soak in? Well, there's a number of different factors that could have led to it not soaking in. We would have had a little bit of a discussion about this in lecture, but I'll lay out some hints. There's nothing to intercept that rainfall. So what happened in this case, for example, was we overwhelmed the system. There was no vegetation to slow rain hitting the surface and seeping into the subsurface. So it just concentrated and ran off before it had time to infiltrate into the subsurface. Now, infiltration is just water access to subsurface regions of soil moisture storage through the penetration of the soil surface. Water finding its way from the surface into the subsurface. Basically all it is. Runoff is the movement of water above and below the surface. There's some nuance there that we'll talk about in a little bit. But it's water that's rushed off, right? It's concentrated on the surface. It's moving as through flow. It's following pathways within the subsurface to a nearby lake or stream or pond, lake, etc. So why didn't the rain soak in here? Well, what about the topography could be influential? Obviously, we see a few different things. There's a bedrock cliff in the background. Rain is on a slope, so it's moving a little bit faster on a sloped gradient. What about the material the soil itself is made of that might be influential? Well, we see there are likely some fine grained material in here, maybe some clays and silts that might be reducing our what we call infiltration capacity, so the ability of that water to soak in. What about the precipitation? Well, if it rained really hard, there's less time for that water to soak in than before the system would be overwhelmed than if it rained nice and easy over a longer period of time. So if you have the same amount of rain, we'll say an inch of rain that falls in an hour, you're going to overwhelm that system really, really fast. But if you have an inch of rain that falls over a day, a nice soaking rain that allows things to soak into the groundwater, that's how you're going to be a little bit more nice, we'll say, to systems like this that are prone to things like erosion and runoff. So we consider soil water in terms of inputs, storage, and outputs, a system. This is our system's approach to geography and to our environmental world around us. So water in soils, how does water get into the soil? Well, it infiltrates. Now, the difference, again, between infiltration and runoff has to deal with the intensity and duration of rainfall, the amount of water already in the soil, the nature of the surface material, the slope of the land, and the amount and type of vegetation. These are all crucial components to understand whether water is going to soak in or it's going to just run off the surface. Now, in these examples here on the left where we see all the trees, we have more infiltration. Why? Well, there's a few different things going on here. The leaves of the trees, for example, are intercepting that rainfall and causing it to hit the leaf and then maybe run off the leaf or run down the branch. It's taking longer for that water to move through the canopy of those trees and the underneath or the under canopy, the subcanopy there, to get to the actual surface. So it takes longer for that to happen. If it takes longer for that to happen, less of it is being basically delivered to the surface over a period of time. And if you have that, you have the ability of that surface to soak that water in more effectively. On the other side, we don't see vegetation. There's less infiltration, more sediment being deposited at the base of that slope, more runoff, more sediment transport, all of these nasty things that lead to erosion that we don't really want to see. Now, if we look at Eau Claire, infiltration is somewhere between 9 and 10 inches per year is what we typically see. We're in that blue, the lighter blue, more or less right about there. That little dot is. Sketch it a little bit more. So we see about 9 to 10 inches of infiltration per year and about 5 to 20 inches of runoff per year, depending on the season. So, all right, how much water can be stored in our soil? Well, that's a concept we call available soil water. And how does water get back out of the soils and where does it go? That's another question we're going to answer here soon. And what happens when soil storage is full? Well, that's a state we call saturation. So let's learn a little bit about these concepts in a little bit greater detail. All right, first off, how does water actually get into soil? What controls water movement? Well, capillary forces. Remember these forces that we talked about in the first lecture? These combined adhesive and cohesive forces. Water likes to snap with other water. It also likes to adhere to other things. So water loves cohesion and adhesion. It likes to be attached to other water. It likes to be attached to other things. Because of that, water moves into our subsurface. It doesn't just sit there. So these capillary forces are very important. They're also important to things like water moving up the trunk of a tree to hydrate a tree or vegetation in general. Now, saturated conditions are those where you have water filling all of the pore spaces within your soil and gravity is moving that water away. So we'll see saturation in comparison to its two other states of soil moisture here in just a couple of slides. So water movement below ground is really dependent on a few different things. The slope of the water table, hydraulic conductivity, or something we call permeability, and the porosity of the material. An aquifer is just a place where water is being stored, congregated within the subsurface. Now, this is just looking at porosity and, again, hydraulic conductivity or permeability within our subsurface. If we consider grain sizes, and we'll see these on the next slide, clays are our really, really tiny stuff. Gravel, and we're going up from there. So we can look at, for example, a clay has about 50% porosity, which means that 50% of the volume is pore space, empty space, and another 50% is taken up by the sediment, clay in this example. And as you move up, sands, gravels and sands, sandstones, dense limestones or shales and granites, we're progressing to smaller and smaller and smaller porosity. If you look at a granite, this really dense metamorphosed rock, right? There's not much space for water to move in there, and really at all. Sandstone, another rock, water can move into. It actually serve as a really good aquifer. We'll talk about why here in a little bit. Now, if we look at hydraulic conductivity, a little bit different. So things like gravel, which have decent porosity and a lot of weird shapes and spaces, water can zip through that at 205 meters per day in some cases. Clays, 4/100ths of a meter per day. 4 centimeters per day is all it can really move. Granites, dense limestones or shales, kind of the same. Dense limestones or shales, 4 centimeters. Granites, 4 millimeters per day. So for porosity, we think of it as how much can you put in. It's the total volume of available pore space in soil or sediment. Now, let's think of it in terms of a cup. A cup here. If we were dealing with clay, for example, I could fill this cup full of clay all the way to the top. And 50% of the volume of this cup would be occupied by sediment. I could fill another 50% to the top with water. So half of the volume would be clay, half of the volume would be water. If I was to take sand, on the other hand, and which has a porosity of 25%, I would fill it to the top. 75% of the volume would be occupied by sand. 25% would be occupied by water. So if we think of how much water can fill in certain types of sediment, certain soils, it's all driven by porosity and permeability. In this case, clay is a lot more porous. There's more pore space. Sand, a lot less so. Permeability, on the other hand, is basically, think of it as how fast can water move in and out of a material. It's the ability of a soil or sediment to allow water to pass through it. In this case, sand is more permeable. Based on the shapes of your grains, their density, all these types of things, water can move in and find pathways through sand a lot more effectively, even though there's less pore space than clay, which is a lot less permeable. It takes a lot longer for water to find its way through clay than sand. Now let's see what that looks like. So here we can see two examples. The top is permeability, the bottom is porosity. Just two simple examples. So if we look at porosity, for example, at high porosity, we see all these grains that are nearly the same size as the pore space around it, right? 50% pore space if we were thinking of this as a clay. Now look at the low porosity, the one all the way on the right there. Most of that's occupied by grains, and little tiny spaces are occupied by pore space. Now let's look at permeability. On the top there, high permeability, you've got things like sands. Water has the ability to move through these granular spaces a lot more easily than low permeability things, where you can start filling in all of these gaps with other things, smaller sediments. Or if we were looking at it just clays, think how dense it would and tough it would be for water to work its way through something that looks like that high porosity scenario versus one that looks like the high permeability or even the low permeability. So as you go from bigger grains to smaller grains, water has a lot more spaces that it has to wiggle through to move through that, rather than the big grains where it can find nice, easy pathways. So this brings us to our soil moisture states, which are really based on these types of characteristics of porosity and permeability. I said this was more we're coming to add to this, so here they are. We've got three primary states. We've got saturation. All pores are full of water, and gravitational water is lost. So water moving into the force of gravity is lost to the system, but all of those pore spaces are full. Think of this as the groundwater table, and water moving through, fully saturating this region. Things are lost by forces of gravity. Then we got field capacity, and field capacity is the available water for plant growth. Not all of the pore spaces are filled. There's some gaps. Capillary forces are the dominant driver, these forces of adhesion and cohesion that allow water to move against the forces of gravity, for example. And then you've got wilting point. This is the point where, through what we call hygroscopic forces, so very, very small forces that are binding water to, for example, the edge of our grains, and we're looking at grains here in these little pictures. Plants can't get at that. If you're below wilting point, your plants are going to start exhibiting that. They're going to start wilting. So for a definition, gravitational forces are the portion of surplus water that percolates downward from the capillary zone, pulled down by gravity. Capillary forces are soil moisture, mostly accessible to plant roots, held in soil by cohesion and adhesion. How do you figure this out? Well, you take the field capacity, another definition. There's a lot of definitions today, so I apologize. Minus the permanent wilting point, that gives you the available water. We'll do some examples of that here in a few slides. And then you've got your hygroscopic forces. This is the portion of soil moisture bound so tightly to each soil particle that it is unavailable to plant roots. This is left after reaching the wilting point. So we have our three states: our saturated state, our field capacity state, and our permanent wilting point. There's one more thing we need to consider, and that's available soil water. So if we were to look at this, which one would have the highest permeability? Well, we already know that. It's going to be our sand, right? Down in the bottom left corner there. What would have the highest porosity? We know that too. That would be our clays. The most available water? That's an interesting question. There are some things that will tell us that. We want to have something that can hold a lot of water and has a low wilting point. We'll see what that is here on the next little slide. We're going to draw a diagram in just a minute here. which has the highest field capacity, so the highest amount of water that something can hold. Again, we're going to talk about that, but what would it be? And then what has the highest permanent wilting point? So let's think about all of these and try and understand what would be driving them. Now, it's not going to be sand, silt, or clay on its own, except for obviously the permeability and porosity. For the bottom three bullets there, it's going to have to be a combination. You need sand and silts and clays and some combination therein to attain these certain types of conditions. All right, so we're going to draw this out here. So pause the video, draw this diagram out here, and once you've drawn it out, go ahead and resume the video and I'll start talking at you again. So I'm going to stare at you awkwardly for about 5 seconds here. All right, I'm assuming you listened to me and sketched this out. You're going to want to know this one. Let me just put that out there. You're not going to need to know all of the numbers. You're going to need to know the concepts off of this one. So make sure we're paying attention here. So in this little diagram, we're looking at the available water per vertical unit of soil, in metric on the left and standard US gross dimensions on the right, inches and feet. It's fine. On the left, on the bottom, on our horizontal axis, we see sand, sandy loam, loam, silt loam, clay loam, and clay. These are all versions and combinations of sediment in some way, shape, or form. Sands and clays being pure, like pure sand, pure clay, and everything else being some mixture therein. We're going to learn a lot more about these when we get to our soil component and we get to the soil lab a little bit later on in the semester. But for now, we're going to understand that these middle four are combinations of sands, silts, and clays. So the top line there, that's our field capacity. That's the amount of water the field can hold. Low in the sand, makes sense. Water is just moving through. High in the clay because it's holding the most, it has the most pore space, it's holding the most water. For our wilting point, follows the exact same trend. Sand, the lowest, again, it's moving through the fastest, so that makes sense. Our clay has the ability to hold the most, so again, it makes sense that it would be the highest. But we notice these lines differ, and they're arcuate, right? They aren't straight lines. Now, if we look at our unavailable water, that is water that plants cannot access underneath the permanent wilting point. They're just locked out of it. It's bound tight through those hygroscopic forces. Above that, above field capacity, you're fully saturated. In the middle there, that's our available water between field capacity and the permanent wilting point. So what holds the highest? What has the highest available water? Well, if we look at this, and I'll draw a little sketch here, it would be the one with the greatest difference between field capacity and our wilting point, somewhere around a loam to a silt loam. What has the lowest? Well, either sands or clays, probably sands it looks like, and mixtures therein. So based on this graph, which soil texture can hold the most water against the forces of gravity? Which can hold the least water against the forces of gravity? Well, sand, it's just going to be rushing out. Can hold the most water would be clays, things like that. Which has the most water bound to soil solids too tightly? Well, you're going to look at what has the highest amount of hygroscopic forces. Again, it would be clays. Which has the least water bound, likely be sands. Which has the most available water, something like a loam. And then which texture would you pick to be great for farming? A practical application. Again, that would be something like a loam or a silt loam, a big combination of all of them where you have high available water, the most water that your plants can use to grow and do happy plant things. Now, Wisconsin here, or Wisconsinites, we have a official state animal, badger, beverage, milk, dance, polka, The fossil is the trilobite. The fruit might be a cranberry. Pastry, I think, is the kringle. Tree, the tree and the dog stump me. Can't remember those off the top of my head. We also have a state soil. Most states do. Ours is this beautiful, beautiful soil that you see on the left-hand side here. I don't expect you to know much about soil yet because we haven't got there. We're definitely going to be talking about this more once we get to our soil section. Now, this soil covers a good chunk of the northern portion of the state. It doesn't creep necessarily into Eau Claire, but it's up in Chippewa County and kind of extends through east, through just north of Wausau, Menominee counties. Anyone know what it is? I would be excited if you did, and I will ask you in person when we get to the soils lecture. But it's the Antigo Silt Loam. Now, there's a video, the Antigo Silt Loam song, that I will be playing, so prepare for that. It is a wonderful song that I hope gets stuck in your head as much as it does mine. I am not going to sing it for you, but here are the verses on the left-hand side here. It's the Antigo Silt Loam, a soil to know, as the verses start. So bear with me. Go watch it if you want, or don't. Don't spoil yourself for lecture. This is where we have fun. Started trying to play. I didn't want that to happen. That's okay. All right, so infiltration and runoff. Soils are the great water gatekeeper, if you will. They control how much water soaks in, infiltration, versus how much runs off, runoff, which causes erosion and flash flooding. They control how much water is held by capillary forces, so the available soil water minus the water extracted by plants. And they control how much free or gravitational water can recharge or percolate to the groundwater zone. Recall that our soil pores must be saturated to be groundwater. All right, so let's continue our little diagram here. Remember, if you saw on that diagram, I said leave some space above it. So porosity, we can add this, a nice simple way to remember it, increases from sand to clay. Capillarity, or our capillary forces, also increase from sand to clay. Our permeability increases from clay to sand. So now that we've kind of put it all together, have this on your diagram, know it, be able to answer questions off of it based off of what we really answered on that slide previously. So that's kind of it for the surface water stuff. Let's switch gears a little bit to our groundwater section.